Central Asia's hydrocarbon and geothermal resources offer a powerful new pathway for supplying critical minerals essential to the global energy transition.
This session, organised in collaboration with the University of Oxford, will showcase real-world applications from companies translating this proven technology into practice.
Discover how revenue streams can potentially exceed traditional hard rock mining values, and how existing oil and gas infrastructure can transform Central Asian nations into global leaders in critical mineral supply.
This is a ready-for-scale opportunity to fuel the next industrial revolution while ensuring environmental responsibility and major economic returns.
Good evening, ladies and gentlemen. I'm Konstantin, and I'm a DPhil researcher at the University of Oxford. We can start with my presentation. While it's firing up, it's a pleasure to welcome you to this session, Turning Brine into Value, a topic that stands at the intersection of scientific innovation, economic strategy, and the global energy transition. First of all, big thanks to Artur Polikov and the MINEX team for allowing us to showcase our research. Today, I want to explore a transformative opportunity for Central Asia, one that can unlock new revenue streams, strengthen mineral security, and position the region as a leader in the next generation of critical mineral supply. This session will showcase innovations developed at the Oxford University in the field of natural resources, ideas, technologies, and research directions that are rapidly moving from the laboratory into industrial deployment. Global demand for critical minerals is accelerating faster than any point in modern history. Well-known lithium and rare earths, newly famous germanium and antimony, and other elements are supporting a selection of strategic industries foundational for modern society. As our technologies become more complex, the number of materials we rely on is increasing dramatically. While base metals remain essential, the supply diversity protects them from risk classification. Yet, long-term projections still raise concerns. Discoveries of large new deposits are declining and grades continue to fall. This morning, we heard excellent discussions on Central Asia's role in diversifying the supply. However, even with the diversification, a hard truth remains. Traditional mining alone might struggle to meet the future demand. Relative to most other industries, mining can be considered as a slow, capital-intensive, geologically constrained industry, but most importantly, fundamentally rooted in the logic of the Industrial Revolution. To meet 21st century needs, we need new resource concepts and new extraction pathways. At the University of Oxford, we are deeply committed to developing such solutions. Oxford generates more spin-out companies than any other university in the UK or European Union, and is home to technologies that have reshaped global industries, from AstraZeneca COVID-19 vaccine to transplantology startup OrganOx, which was recently acquired for $1.5 billion. Building on this environment, we launched the Oxford Earth program this year, an interdisciplinary initiative spanning across 9 departments, from earth sciences and engineering to history and law. Our mission is simple but ambitious: to rethink how the world sources, processes, and uses critical minerals. This includes new extraction technologies, new geoscientific frameworks, and entirely new classes of resources. Essentially, traditional mining is an attempt to reverse engineer natural processes of mineral formation. Natural geofluids mobilize metals, transport them, and concentrate them into deposits that we later mine. The mining industry has made a tremendous progress in safety and environmental performance, yet the conceptual basis remains unchanged since the 19th century. We excavate hard rock, we discard 90% of it as a waste, and dissolve ore back into the fluids to then selectively extract the metals, effectively recreating natural geofluid chemistry in a processing plant. Across the world, scientists and engineers are now pursuing a different idea, producing critical minerals directly from fluids, from geothermal water, reinjection streams, oilfield brines, and mine waste. Techniques such as direct metal capture, scale extraction, and advanced separation process have now reached pilot and industrial scale. These approaches create a totally different pathway, low-impact, high-value metal extraction that leverage existing energy infrastructure rather than disrupting it. This brings us to the idea of saline geofluids, a unified term we use for modern subsurface fluids with a mineral potential. These are the same fluids currently disposed of as a waste in oil fields or reinjected in geothermal plants. Yet chemically, many are enriched in high-value elements: lithium, bromine, iodine, rare earths, gallium, germanium, and others. Favorable conditions for saline geofluids exist worldwide, and importantly, they rely on the infrastructure that already exists. We are reframing brines not as a disposal challenge, but as one of the world's largest untapped, unconventional mineral resources. The idea first appeared long ago. In the mid-1950s, facing a national bromine shortage, the United States analyzed brine in a small decommissioned oil field in Arkansas. The fluids contained bromine at a concentration 70 times higher than those of seawater. Within years, America became the world's second largest brine exporter. Today, the same brines are used to produce lithium, strontium, and iodine, supported by the advances in separation chemistry. Geothermal fields across the U.S. now produce significant quantities of critical minerals alongside power generation, often with revenue streams exceeding or at least equal those to the electricity revenue streams. We can now extract metals at part per million concentrations from a large volume of fluids selectively and efficiently, all thanks to the breakthrough in separation science. The economics depend on balance of flow rate, concentration, reservoir conditions, complexity, and we are aiming to find this sweet spot you can see on the graph over there. Conceptually, brine extraction is compelling. It's minimal surface disruption, shorter development timelines, lower energy use, and no tailings or large volume waste. It will never replace a hard rock mining, but it offers a complementary pathway, particularly suited for the agile multi-metal supply chains that are required for advanced technologies. Today, brine-based extraction is already operating at scale. The Salton Sea in the United States, the Oaxaca geothermal field in New Zealand, and the lithium triangle in South America. A simple model multiplying metal concentration in brines by flow rates and discounting for extraction recovery efficiency lets us estimate annual metal flux that helps evaluate the resource potential of a single well or an entire field. Preliminary estimations derived from open source data showcase strategic resources of crucial minerals and extremely large revenue rates. American geothermal and oil field brine annual metal flux translate in $11 billion per year, while a small geothermal field in New Zealand pumps through the heat plant about 10% of global demand for tellurium, which together with other metals has a combined annual revenue of $300 million per year. Central Asia, and not just uniquely positioned to help diversify the supply chain, it also has one of the world's most favorable conditions for this resource type. Kazakhstan alone hosts over 40,000 wells and an extensive reinjection networks. Its Paleozoic and Mesozoic basins contain highly saline fluids enriched in bromine, iodine, lithium, strontium, and potentially rare earth metals. Uzbekistan and Turkmenistan contain deep basins with iodine and boron-rich brines, while Kyrgyzstan and Tajikistan host high-temperature geothermal systems with fluids capable of carrying silica, lithium, and rare earths. If the potential is so large, so why has development been limited? Historically, capital costs are high, commodity prices volatile, and the energy and mining sectors rarely collaborate. Investors avoid multi-commodity deposits, and regulatory frameworks are not designed for brine-derived minerals. That's the issue we'll address in the closing talk of our session by my colleague here, Dr. Metehan Çiftçi. The highlight, however, is that knowledge gaps exist and of a considerable size. For example, the spatial variation in metal concentration across brine within one field, absence of time series geochemical data to dynamically assess ultra-trace endowments. This is just a few examples of research challenges and questions we are trying to investigate and we are working on at this time. Now, before I close, I want to highlight that what I've presented today is only the beginning of a much larger story. Oxford is a home to a growing portfolio of technologies and companies translating this science into real-world impact. Immediately after my speech, you will hear from two teams who are already moving beyond research, Ascension and Siloxium, companies that are pioneers in their fields, and I'm very excited to hear what they have to say. To conclude, though, I would just like to reiterate on a few main topics. The global economy, and you all are aware of that, urgently needs new sources of critical minerals. And saline geofluids offer a pathway that is scalable, fast to deploy, and environmentally responsible. Here at Oxford and in the United Kingdom, we're trying to be a hub for the innovation and new ideas that will be later translated into the industry solutions. If embraced, Central Asia can position itself not just as a supplier, but as a global leader in the next generation of critical mineral production derived from brines. Thank you, and we'll have a joint Q&A session with all the presenters at the end of the session. Now we'll be joined by Dr. Michal Perev, joining us online to present a research in Ascension on sourcing rare earth minerals from the volcanic brines.
Thanks, Konstantin. Can you hear me?
Yes, we can hear you.
Okay, I will just share my screen. All right. Can you see that?
Yes, all good.
Okay, great. Thank you. Okay. So hi everyone. My name is Michal Camejo, and I am the lead geoanalyst for a company called Ascension Earth Resources. We are a spin-out company from the Department of Earth Sciences, University of Oxford, and we spun out just over 18 months ago. And we are aiming to commercialize new technologies for extracting critical metals from previously untapped volcanic environments using active geothermal systems. So I'll go on to explain the basis for our approach and how we aim to do this. So the majority of the non-ferrous metals that we extract in mining are ultimately linked to magma in some way, whether through primary igneous processes or secondary processes such as weathering that concentrates the natural mineral assemblages in these rocks. And certain volcanic settings produce deposits that enrich in critical materials, and then magmatic enrichment processes can form potentially economic ore deposits. So if we think about a subvolcanic system beneath a volcano, and you have one of those volcanic settings that is able to produce those deposits that are enriched in critical materials, such as continental rift, for example, which produces, in many cases, alkaline parent magmas. You can imagine that when these magmas percolate through the crust, they evolve and fractionate, and the metals that were originally in those parent magmas can concentrate in the following ways. When crystals precipitate from those melts, those metals get trapped in the crystals, and the residual melts evolve, and in the same way, critical metals are trapped in the melt. And beneath the crust, you would have areas that are crystal rich and areas that are melt rich, and conventional mining tends to utilize those crystal rich areas. So these are called intrusive rocks, and we mine areas that have layered intrusions that represent these types of rocks and granites, for example. These are the traditionally mined regions of rock from these igneous systems. A complementary magmatic deposit, extrusive rocks, which are felsic volcanic rocks. These are the melt-rich equivalents. These also contain relatively high concentrations of these critical metals, but they aren't conventionally mined. So in terms of conventional critical mineral recovery, it generally tends to be inefficient and damaging. as we've heard in previous talks, if we have an intrusive ore-bearing rock, in this example, you have eudialyte, which is the pink area of these rocks. First of all, you would have to find these ore bodies, which isn't always easy to find. Then you have to get the minerals out of this ground in some way, whether through subsurface mining or open pit mining. So this leaves a huge environmental footprint. Then the metals that are trapped in these minerals are often difficult to unlock. So it requires an energy-intensive process to get the metals out. So it includes crushing and milling, and then often involves the use of harmful chemicals to extract these metals out of certain minerals. So the melt-based equivalent rocks to these rocks that are traditionally mined also have high concentrations of critical materials in extrusive igneous rocks. And these form through large magnitude eruptions where magma can rise up to 20 kilometers into the atmosphere and cool very rapidly to form a glassy type of igneous rock. So these are the melt-based equivalents. And under those circumstances I mentioned earlier, these rocks will have high concentrations of critical metals. And this represents a new category of a uniform quality resource with vast economic potential. So essentially, this is a large untapped resource, and it's globally spread. So once we know the tectonic settings that these types of magmas and eruptions tend to form in, we can sort of map where in the world that we're likely to find these types of rocks. And as Ascension, we're trying to recover these metals from these previously unexplored geological resources, providing the potential to establish supply chains that are drastic departures from the existing ones. And if we want to compare the extent of this resource to conventional mining, we have this example here that's drawn to scale on the slide. So we have the approximate volume from a carbonatite mine in Mountain Pass, USA, compared to a target resource from a single volcano that will erupt these vast deposits of explosive eruptions over geological time, so thousands to millions of years. So you can see the comparison of the deposit. One caveat here is that this is a low-grade ore that we're talking about, but at Ascension we are developing a technology to extract the metals from this vast deposit. So this is a novel geothermal in-situ recovery process to sustainably extract these critical minerals from volcanic glass. So we would first find these naturally extensive volcanic rock deposits that were deposited over geological time beneath the surface. Again, we would know where to find these deposits based on tectonic settings and where we would expect to find these magma compositions. And then we would employ in-situ leaching or solution mining, which is currently used in uranium and copper mining. So essentially, we would inject our proprietary leaching solution and dissolve the critical minerals from the rock layer, and then pump out the resulting pregnant leach solution onto the surface for processing. And it's a closed loop system, so after the metals are extracted from the solution, we then re-inject it back into the deposit, and creating a continuous cycle. One difference here is that we are using geothermal heat to help with the leaching process. So we are targeting areas that have active geothermal systems, where there are often established geothermal power plants, to help with the energy needs associated with this system. And because of how our technology is set out, we're going to skip all of those environmentally damaging aspects to the mining process and go straight to leaching and separation. So at Ascension, we have this comprehensive end-to-end technological solution to optimize in-situ leaching. So our expertise spans geological and geothermal analysis, so that to map where the areas are that overlap with the right rocks and the geothermal heat. And then we will use geophysical methods to detect and monitor how the fluids are injected beneath the surface. We have reservoir modeling engineers to help with the designs for optimal well configuration. And then we have geochemists who develop the recipient to optimize the target rocks for subsurface fluid flow. And then we will partner with other partners in the industry, like Luxium, for example, to try and separate the metals from the pregnant lead solution. One thing to note here with the rock targets that we have of interest is that we aim to recover a suite of minerals that are not just limited to rare earth elements. So of course our target are the rare earth elements, but we are also able to recover other critical metals from these rocks as the metals tend to be hosted within the glass. And if we compare the rocks that we have of interest to other mining deposits or deposits such as carbonatites, for example, carbonatites have a higher ratio of light rare earth elements to heavies, whereas alkaline glassy volcanic rocks tend to have a higher ratio of heavy rare earth elements to lights. And we know that these heavies are what are necessary to make those permanent magnets that are necessary for the defense and clean energy applications. So at Ascension, we are uniquely positioned to transform the critical supply chain. We have a proprietary technology that we're developing in the form of geothermal in situ recovery, and we have a world-class team that is positioned to do so. And because we keep our minerals in solution throughout, we eliminate intermediaries and reduce the cost and impact. We have a value chain added advantage. So I'd like to end here and thank you for your attention.
Thank you very much, Michal. Thanks for this exciting talk. And now let's welcome Richard Dixon to speak more about the separation science advancements held at Oxford.
Thank you. Good afternoon. Thanks for the opportunity to be able to share our story with you. Thank you, Constantine from Oxford University. And the link is that we are a startup that came from Oxford University, and we're 3 years old. Today's my first year anniversary, so a fortunate coincidence. This work started at Oxford University with Professor Nick Hankins, looking for a low carbon footprint way to clean up streams such as acid mine drainage. Along the way, they discovered that the technology can do infinitely more than that. And so what I'll do today is just share a few examples. Personally, I grew up in a mining camp, copper in central Chile, South America, and have been around mining most of my career. If you would have told me 5 years ago that I'm now looking forward to spending a lot of time in Kazakhstan and Central Asia, I would have thought you were nuts, but that's the way it's going to be. So I'll just dive right into it. So for next slide. So basically, I'm just going to go very, very high level. Happy to talk with you about more of these applications. But basically, Luxium has developed a platform of water-soluble polymers that are modified. So it's kind of like an ion exchange resin, where it's a soluble polymer that contains the functionality of ion exchange resins. So what that does is that it makes the kinetics of capture extremely fast. It's very scalable, very robust, can tolerate pH changes, even organic solvents in the mix, and is applicable to several metals. And then we can tune the functionality of the polymers to capture different metals and other species. So our playing field then can capture value along all of the metal chain from mining to end of life disposal. As I mentioned, we can have aqueous streams. They can have substantial amounts of organics in them, solids. And so far, the target metals that we've worked most on are listed here, particularly palladium, gold, copper, etc. Concentrations lowest around maybe 5-10 ppm for gold, even 0.2 ppm we can successfully recover. And that in a background, a very high level of impurities such as iron, which is always around everything, and other impurities, even at ranges around 50 to 100 gram per liter. In the background, we can successfully separate minor metals from those. So this has nothing to do with mining, but it shows one of the applications, which is recovering precious metals from homogeneous catalysts. We can recover a lot more palladium from homogeneous catalysts, which are used by pharmaceutical companies and agrochemical companies to manufacture active ingredients. And we can do that with significantly lower reagent consumption and speed compared to current technology, which typically is ion exchange. So this is our pilot plant in Teesside, capable of operating at about 1 ton per day. So even though we're only 3 years old, we've actually been moved quite fast in terms of being able to scale the technology. This is at around TRL 8, so we're now working at our first commercial application, pretty close to signing a multi-year contract with this one. Gold is another important one, particularly near to my heart because of mining. As I mentioned, we can recover gold at levels of 0.2 ppm in cyanide solution, so either extremely acid as the palladium case or extremely alkaline as the gold case, with very good recoveries and in the presence of other impurities. So this is at about TRL 6, and we are working on applications for field trials on this one. Just more detail on the gold application. I think that I'll just skip over that one. Rare earths is one that we got into a little bit fortuitously, which is because we applied for a grant to work on rare earths. I think it's just at the beginning of the boom of funding that's coming out for rare earths and critical metals. But anyway, we thought, why don't we try to use Selectal technology to separate individual rare earths one from another, which is traditionally quite difficult to do, requires multi-step solvent extraction and other technologies. And interestingly, what we can do is we can capture all rare earths in bulk and separate them from high background metals like iron, aluminum, etc. But much more interestingly, something we discovered only a few months ago, we can take out uranium and thorium selectively from that rare earth stream and isolate them at the beginning of the process. We think this is going to be quite, we'll be able to take this quite far, because that means that you can extract more rare earths from the same deposit, or you can avoid regulatory issues in processing rare earth streams. So basically, advantages of the technology: we can separate metals of choice from high background level activity, very high hydraulic throughput, very simple infrastructure requirements. You need basically one mixing tank, another mixing tank, and a filter press, and away you go. So very simple in terms of infrastructure. All the knowledge, all the technology is in the polymers themselves. We can recover several species and tolerate quite a variety of conditions. So just to recap, we use polymers that are modified with functional groups very similar to those used in ion exchange resins. We get some additional selectivity from know-how and some modifier additives. And we're currently developing partnerships to validate this technology and tested customer sites and tried different metals that we haven't already tried. So thank you very much. Appreciate it.
Thank you very much, Richard. Now we'll welcome here Dr. Çiftçi Mete, who will speak to you about the research in the direction of legal and societal issues and the absence of the framework for the new resource development.
Can I stay here? Is that? Yes. Yeah. Thank you. That will facilitate the panel discussion, I hope. My name is Mete, and I'm one of the researchers, one of the social scientists on our project called Reset. And at Reset, we are having a kind of like a novel approach to mining, as Konstantin explained the technical details of it. And so it's a very different approach. We're talking about not waiting for minerals to form up after volcanoes erupt and millions of years pass. We're talking about capturing them at elemental stages while they're still dissolved in the brines. And this might also bring opportunities for co-recovery of geothermal energy and the metals within, because we need the cool brines, and we can maybe capture them after the energy, the heat has already been extracted from them. So in that regard, it's a novel approach, and there are so many, it comes with a lot of opportunities, but also, as Konstantin explained, it comes with challenges. And it is happening, though. We're not, crazy scientists or anything. It is happening, and but you might ask the question of why it's not, we're not taking the place of conventional mining approach as well. There are quite a few reasons, and I'm going to talk about it, but time is short, so maybe we can also talk at the drinks. So my presentation, my speech, will be grounded in my research on Montserrat in the West Indies. So we're focusing on the Eastern Caribbean volcanic region for our research and exploring the potential of the mineral potential of the brines there. So and we have a lot to learn from the case of Montserrat and our research on Montserrat. It's a small island, but it does teach us a lot of things. And in that sense, I can say basically a key takeaway would be that even when the geology is promising, institutions, governance, and public trust, these kinds of aspects usually ultimately determine the project's success. So we will be talking about maybe preliminary results. And a key point that came out in the discussions that we had in Montserrat and elsewhere is the legal uncertainties and making it clear what counts as a mineral. So when you try to apply these kinds of novel approaches, this comes as it's a funny question to ask, but this comes up as a key issue, because in Montserrat, for example, the Geothermal Act defines geothermal resources in many different ways, but it explicitly says that they're not mineral resources. And this is not very uncommon. In so many contexts, legally speaking, the condition of these brines can be questionable. So I tried to do some research on this in the context of Central Asia. But I think in Kazakhstan and Turkmenistan, this could be an interesting approach to consider, because there are so many decommissioned oil fields there. But whether the brines that will fill up these spaces, will they be considered as waste? Should they be out of any mining operations? Should they be considered outside of any mining operations, or can they be treated as another mineral resource? This could raise new questions, and this is why we need more clarifications about novel approaches to mining. and ambiguity often invites litigation. So for our project, we looked at Texan, the case of Texan oil fields. I think that's quite relevant to this discussion. I mean, of course, it's a whole different kind of jurisdiction, but when you look at the cases, legal cases that already emerged in the direct lithium operations going on in Texas, you can see that the legal ownership of these oil fields raises a lot of questions. Like, is it the oil companies who still own the brines there after leaving those oil fields for decades, or is it now? Can the mining companies claim ownership through their deals with the states? So these kinds of issues can sometimes delay or even halt the projects in the long run. In the case of Montserrat, also procurement is an interesting legal aspect. So some of the legal experts we've spoken to, they raised their concerns about the lack of expertise, the limited expertise in these contexts. The expertise that they have doesn't really meet the requirements of such technical novel approaches. And this often endangers the tendering processes, where the mining companies or geothermal companies cannot really find the common ground with the basically public officials. And hybrid contracts. So some legal experts suggested creating flexible contractual models tailored to geothermal or like brine mining co-production, rather than forcing developers into ill-fitting mining or energy templates. Because as Konstantin briefly touched upon, in the context of geothermal mining, where co-recovery, we're talking about mining companies working with energy companies, which is in and out of itself kind of a challenge alongside an opportunity, because who is going to have the final say on these projects? Who is going to make the decisions, basically? And we have seen in the first commercial geothermal mining project that was established in Salton Sea in the US, how it led to complications. Happy to talk about its details. And international financial assistance is often key in the context of the Caribbean countries. It was. Most of the progressing mining projects or geothermal energy projects, they have been supported by international organizations like World Bank or Caribbean Development Bank. In the context of Central Asia, I think, again, World Bank, but also Asian Development Bank, and these or like governments who have expertise on geothermal could be key. So I think, and finally, the community trust and social license. These are also key issues, and when the communities don't have the trust in the processes, it can lead to complications. In Montserrat, there are lots of concerns about leading a public-private partnership project. Instead of or like build, operate, transfer kinds of models receive quite a lot of skepticism. So it is important to address these kinds of concerns alongside some maybe concerns that can sound absurd, like is this project going to lead to a volcanic eruption? Is this going to lead to earthquakes or fracking? These are all kinds of questions that we often face, and we need to address all of them with full attention, I think, instead of ignoring them. So I think the case of Montserrat shows that you can have the wells, which are there now. You can have the minerals. You can even have the political will and interest, but without clear laws, credible long-term contracts, procurement expertise, community trust, and a plan for economic integration, the resources remain untapped. And in Central Asia, with its massive former oil fields and brine or geothermal potentials, this is this is a key kind of like maybe we're standing at a crossroads in terms of achieving like maybe going down a similar road of extended processes of tendering, or maybe achieving a co-recovery of geothermal energy and brine-based mineral extraction. So, thank you.
Yeah, thank you, Mete, and we'll go to the Q&A session. However, before that, I'd like to quickly reiterate on what Mete just said. And yeah, a small island nation shows us an example of what to expect when we try to drive this innovation into bigger regions, bigger countries with a massive existing infrastructure. And the two most common and most critical challenges that we face is the industry's reluctance. Again, oilfield energy companies, they don't concern themselves with the critical endowment, with the mineral endowment of the brines that they're pumping through their infrastructure, together with the absence of expertise and frameworks from the policy making side. And there's a big research group trying to tackle these issues. However, we are in the beginning of this journey. And now I'll take the questions from the audience, if there's any. Seems like there are no questions, and you all look very drowned up from energy. It's quite late at the evening. So thank you so much for joining us today, and I hope we gave you some exciting insights on the research happening at Oxford. Thank you.